Hi, this is Dr. Schultz, and I just wanted to share with you one more example of how to use momentum conservation. This problem, though, will be a little bit different because we're going to use momentum conservation and energy conservation. So this is kind of a combo problem. The type of problem is a typical one in physics. It's called the Ballistic Pendulum. It's kind of a cool name. So the situation would be that you've got something like an apple, we'll say, that's hanging from a string. So there's your apple. And then you're going to have some other object, like maybe a dart, that's going to come in and it's going to move in and it's going to collide and stick with the apple. Okay? And what's going to happen is the two things are going to collide and stick, and then the apple is going to swing back. So we're going to draw a couple more pictures here and kind of show the steps that happen. And we're going to have to decide when we can use momentum conservation, when we can use energy conservation to figure out some stuff about what happens. So why don't we start off with this picture. I'm going to call this kind of A. That'll be our snapshot here at the starting point. And let's say, just to keep the numbers simple, I'm going to make the mass of this bullet or this dart equal to 1 kg. I know that's kind of big, but let's just use 1. And let's make the apple the same thing. So we'll say that it has a mass equal to 1 kg. And then I'm going to have to specify how fast this dart is moving. And so we'll say that it's moving maybe at 4 meters per second to start with. And that gives us kind of an idea of how fast this thing is actually going. Okay, so now let's draw a couple of other sketches of what happens next. I'm going to actually sketch 2 more diagrams, and I'm going to label them B and C. And in B, what I want to show is that B is the instant when the dart lodges in the apple and the apple has not yet started to swing up. So we're going to have the bullet inside, or the dart inside the apple, and now this apple is going to recoil with some velocity v. And that's the reason. This velocity is not going to be the same as the initial velocity, and I hope that you guys can recognize that this type of collision is an inelastic collision. It's a sticking collision. So we're going to have to use some momentum conservation to figure out what that velocity is. After that happens, this whole apple is going to swing up along with the dart, and the center of mass is going to rise up by a height h. Okay, so this whole object is going to swing like a pendulum, and it's going to come up here. It's going to be at rest, at least just for a moment, right? Because that's a turning point. So this height is going to be kind of like the maximum height. I guess you could put a maximum there to indicate that. Okay. So a typical question, one way to go with this would be to find the value of the maximum height. So how high up does this apple swing vertically as a result of this interaction? Okay. And so then what you have to do is look at the situation, and when you go from A to B, you're going to use momentum conservation. So we'll say momentum is conserved. And that's because there's really no net outside force acting on the apple from A to B. You might say that gravity is acting on the apple, and it is, but so is tension, right? And so the two forces, you know, if you drew them out, if this is the apple, you'd have tension going up, you'd have gravity going down. They cancel. And so the net force is actually 0. So it's okay for us to say that momentum is conserved. So let's use that, and we're going to say momentum at A is equal to momentum at B. At A, the momentum is going to be 1 kilogram times plus 4 plus 1 kilogram times 0, that's the apple. So mass times velocity plus mass times velocity. Afterwards, we have a total mass of 2 times some velocity v. Sorry about that. So what you end up with is that 4 is equal to 2v, and your final velocity is 2 meters per second. So we now know that this is 2 meters per second. And that should kind of make sense, right? Because you're doubling the mass in this collision, and each of the masses, have the same value, so when they combine, you would expect the velocity to change by a factor of half. Okay. So then let's finish the problem and go from B to C. And here we're going to use energy conservation. And clearly, momentum is not conserved from B to C, right? Because the object is moving at B, and it's not moving at C. So momentum is totally not conserved here. And the reason is because now those two forces that we talked about do not cancel each other out anymore. Okay? And now you've got a situation where tension goes this way, mg goes that way, and now you've got some type of an F net. And so, so you'd say P is not conserved. Whoops, not conserved. But you can use energy conservation because we can talk about gravitational potential energy changing, and we consider the Earth as part of the system, and that would work. So what I'm going to say here is that my kinetic energy at B is equal to my gravitational potential energy at C. And then I can plug in, at B, it's 1/2 times 2 kgs times the speed of 2 meters per second squared. I'm leaving out the units here. Keep it simple. So 1/2 times the mass of 2 times the velocity of 2 squared. And that's equal to mgh, which is going to be a mass of 2 times gravity of 10 times h max, which we're trying to find. So probably you guys should write the formulas. 1/2 mv squared is equal to mgh, and then just plug in the numbers to show what you're doing. What you end up with is 4 equals 20 times h max, and that means that h max is equal to 4 over 20, which is also 0.2 meters. Right, because 4/20ths is 2/10 is 1/5, and that's your answer. So, kind of to summarize here, what we did with this problem is we had to split this problem into two parts for the ballistic pendulum. We used momentum conservation for the collision part because there was no net external force, and then we had to use energy conservation for the swinging part because there was a change in gravitational potential energy. And then we kind of had to work through those steps. This problem, you can see a lot of variations of this problem, and sometimes what happens is that you're given h max and you're asked to work backwards to find the velocity that the dart would need to reach that h max. And I think you've done a problem like that already in the homework. So just be familiar with working this problem both forwards and backwards, and those are the two steps that you have to take. So have fun with that. We'll see you soon.